these complex numbers then, first thing to say is complex doesn't mean difficult. I think we're going to find that to add, subtract, multiply and divide these things is not that difficult. So it's not that. It's called a complex number because it's got two parts, a real bit and an imaginary bit. And when we come to apply it to things like electronics, the real bit ends up being something like the size of the current, 3 amps, 4 amps. And the imaginary bit turns out to be very good at describing, say, the phase angle of that current with respect to the voltage or something like that. So in AC circuits it becomes invaluable. And both of these parts, the imaginary bit, that you at first sight you might think isn't in fact useful, turns out to be very useful to give us things like the phase difference. In other words, the angle relative to something else, and the real bit tells us the magnitude. So that's the vector representation. A vector has a magnitude, that's given by the real part, and an angle, which is given by the imaginary part. So they're useful. Remember, j is the square root of -1, so that means j squared is -1. So with that in mind, let's have a look at how we can represent these complex numbers. I'll show it to you and then I'll pause while you just write it down. So I'd rather you weren't writing while I was trying to explain it. Let's just have a look at these. There's two systems that we use to represent these complex numbers. So this is a complex number here, vector, that we were looking at before. Here is the same complex number, a vector, but they're both represented on two separate coordinate systems. One is the rectangular coordinate system we've seen already. So how do I represent this complex number? It's the position of that end of the vector. We assume it always starts at the origin, so it's going to end up here. So what's the coordinate? -3 on the x-axis, 2 on the y-axis. So this is going to end up representing the complex number. -3, remember I said that this was the real axis. So -3 on the is the real part, and 2 is going to be the imaginary part. So that's going to have a j associated with it. But in the same way, we can represent our vector on what are called polar coordinate systems. And that's exactly like in the drill. It's giving us a magnitude of the vector, which is the length of this line, r, here, but also an angle. And the angle is always measured, as we've done already, from the positive real axis, anti-clockwise being positive. So I can represent my vector either on the Cartesian or rectangular coordinate system or on the polar coordinate system. If we look at this, this is the complex number on the rectangular coordinate system, -3 on the real axis, 2 on the imaginary axis. How do I know that's the imaginary? Because it's got this j, the imaginary number. So I know that that's going to be a vector going 2 up the imaginary axis and -3 along the x. How do I get it to be in polar form like this? Calculators do that for us. If you look at your calculator, you will see above the plus button, it says POL. So if you hit Shift and then the plus button, you will get the opportunity to put in -3 as your first coordinate. So in the calculator, you put in -3. And then you want the comma, because it's not complex numbers this calculator is doing, it's converting from one coordinate system to another. So it wants this, -3, 2. So you put -3 and then the comma. And if you look at your closed bracket symbol, that's the comma. So Shift, closed bracket will give you the comma. And then you put the 2 in, not J, just the 2. Close the bracket and then hit equals. And you will get the polar coordinate, which should be 3.6, 146 degrees. If you've not got 146 degrees, you might be in radians, so you need to change the degrees. We have I've got this complex number, minus 3 plus 2j. And I want to represent that not in rectangular, but in polar form, this form. And we'll see why that's useful later. It's handy when we come to doing things like add, subtract, multiply, and divide. Sometimes you want to be in polar, sometimes you want to be in rectangular. So how do we convert from one to the other? Minus 3 plus 2j. I put in minus 3, comma, 2. So the shift polar and then that, and then it converts it to this. Note the names. In this polar, this is called the modulus, which is the magnitude of the vector. And this is called, I don't know why, the argument. So the angle is given the name the argument of the vector in polar coordinates, and that's the angle measured from the positive x-axis. So I'll just pause if you want to make a note of that. So I'll stop this video here, in fact, and then I'll look at some examples of how we use them to add, subtract, multiply, and divide in further videos.